Okay, so in this video we'll finish up section 11.4, which is the cross product. So the next thing I'm going to introduce is if A is not the zero vector, B is not the zero vector, and theta is between 0 and pi, is the angle between A and B, then the length of A cross B is equal to the length of A times the length of B times sine of theta. All right, so this is similar to the dot product formula that we have, but notice this is not how you get the cross product. This is how you get the magnitude of the cross product, the length of the cross product. So of course you could compute, if you have the cross product itself, you already know how to compute a magnitude. This is more useful if you want to find the sine of the angle theta between the two vectors, not just find the magnitude of the vector, because we know how to do that already. All right, so let's look at an example. We'll look at number 6 on page 735 of you all's textbook. So, and number 6 says, using the cross product, find the sine of the angle between the vectors A and B in exercise 4. All right, so we did exercise 4 in our last video. The vectors from exercise 4, 3, 4, 12. And B is 3, 4, negative 12. And we already computed the cross product. It was A cross B was the vector 96, and then, it was negative 96, sorry. Negative 96, 72, 0. So they want us to find the sine of the angle between these two vectors. So what we're going to do is we can just solve this equation for sine of theta. So we know the sine of theta is going to be equal to the magnitude of A cross B divided by the magnitude of A times the magnitude of B. So let's find the magnitude or length of A cross B, which is just going to be the square root of negative 96 squared, so 96 squared, whatever that is, plus 72 squared plus 0 squared divided by the magnitude of A times the magnitude of B. Now, the magnitude of A and B are going to be the same thing because they both have the same, the magnitude of their entries. Their entries are the same with the exception of one is 12 and one is negative 12. But that's going to get squared anyway. So the magnitude of A is going to be the square root of 3 squared plus 4 squared. So we have 9 plus the 16 gives us 25 plus 144. So we're going to get the square root of 169. And this, we're also going to get the square root of 169. So we just get, I'm not going to compute that numerator. 96, sorry about that, squared plus 72 squared over 169. That is a 6 right there, sorry. So that's 96 squared plus 72 squared over 169. That is the sine of theta. All right. Next, let's look at how we can determine whether two vectors are parallel. So we talked about the dot product helping us determine whether two vectors are perpendicular. So now the cross product can help us determine if two vectors are parallel or not. So if A is not equal to the 0 vector and B is not equal to the 0 vector, then A and B are parallel if and only if A cross B is equal to the 0 vector. All right, so that's a means by which you can determine whether two vectors are parallel to one another or not. So now remember, vectors can move around in space. So any two vectors that are parallel to one another, these two, for instance, are never going to cross one another. And if we were to compute their cross products, and doesn't matter where they are, they're still parallel. We can move them around no matter what. They will never cross one another unless they're, of course, they're the exact same vector. But so the way that we could determine whether two vectors are parallel without having them visually is just by computing the cross product between the two and seeing do we get the 0 vector. All right. So the next thing we're going to talk about is torque or moment. So consider the force F acting on a rigid body given by the vector PQ. So our rigid body would just be represented by some vector where we have or a line segment, a directed line segment. And now the force is going to act either at P or Q. It's going to act the way we set this up as well. We set up the force acting at the endpoint Q. At the point Q, for example, PQ is a wrench. So there's a good illustration of this in their textbook, but since I'm at home, I have wrenches. So if we had a wrench, now we're saying that this would be Q here. If I'm going to take the wrench and I want to turn something there, the force is going to act on this side. So this would be P over here. This would be Q over here, wherever the force is acting on the wrench. The tendency of the rigid body to rotate around an axis through P that is parallel to PQ cross F. All right, so We have our wrench. We want to turn. We'll pretend that this is a nut that we want to turn with our wrench. So remember, this is P over here. This is Q. So my hand is the force. So let's just say the force is going to go in this direction. So the force is going to push down that way. So now I have a force acting in this downward direction on the wrench. So that's the F. And then we have our vector PQ is the wrench itself. So sorry, PQ is the wrench itself. And then it says the tendency of the rigid body. So the tendency of the wrench to rotate around an axis through P. So this would be an axis through P coming directly out of the page that you are, directly out of the screen that you are. That would be the axis through P. So the tendency of the wrench to rotate through that axis that is parallel to PQ cross F. So remember, PQ cross F, a cross product, is going to be perpendicular both to PQ, and it's also going to be perpendicular to F. So we're rotating around this axis coming out of the page, which is certainly perpendicular to that and perpendicular to that because those are both in the page. So the tendency of a rigid body to want to rotate, basically how easy or difficult is it for this to rotate, my force to rotate this nut or screw, whatever it is that I'm trying to turn. It's called the torque or moment of F, and is given by M equals the vector PQ crossed with the vector F. All right, so we'll look at an example, a torque example. So we're on page 735, we'll look at number 22. And it says, a 5-pound fish hangs from a fishing line on a 4-foot fishing pole, held in an angle of pi/4 with respect to the horizontal. Find the moment M due to the weight of the fish about the handle end of the pole. Okay, so let's see how we'll sketch this way. So here is our fishing pole, and the fishing pole is at an angle of pi/4, yes, with the horizontal. So then the fish is up here, and it's a 5-pound fish. So we have our little fish right here. So we have our 5-pound fish right there. Now, remember I mentioned earlier in the course that whenever you see pounds, that is a force. So that means we have a force, and the force is moving in the downward direction. So we'll draw a little arrow and put 5 pounds right there to indicate the force of that fish in that downward direction. So now what we want to do is they asked us to find the moment M due to the weight of the fish about the handle end of the pole. So here, if we label things the way we had them labeled, or the way that we discussed torque, this would be our Q, would be that end of the pole, and this would be our P. This is the point at which the object is actually turning. So yes, the fish is up here, but the pole, the handle of the pole is going to turn right here. So this is where our wrench was turning, where we actually had the nut itself. And then the force is acting at the other end. So the fish is our force and our turning point is the handle end of the pole. So now to compute M, our moment, it is the vector PQ crossed with our vector F. So we have to figure out what are these two vectors that we have here. So because we're working in 2 dimensions, because we're just looking at the plane that the fish is actually in, we can simplify this. So first let's find the easier of the 2 vectors. Let's find what F is first, because that's the easier one to find. So F now is just this vector. If we had some coordinate axes on here, so if I put a y-axis there and make this an x-axis, we don't necessarily need them, but if we look at this vector right here, it's not going in the x direction at all because it's not moving to the left or to the right. It's going straight down. So its I component is 0. Now its j component is 5. So if we took the unit vector j, because 5 is our magnitude, we would have the unit vector j multiplied by -5, actually not 5. So this is just going to be 0i minus 5j is what that vector right there would be, or just -5j, however you want to write it, or if you want to just write it as 0, -5, that's fine. All right, now the other vector that we're considering is the vector PQ. So we have to find what this vector PQ is. Oh, I forgot to put the length of that pole. It tells us that the pole was a 4-foot pole. So this length here is 4 feet. Now from that, we can use the PQ. So if you remember from an earlier lesson, I'll write it out again. It is the magnitude of PQ times cosine of theta, where our theta is going to be pi over 4, I, plus the magnitude of PQ times sine of theta, j. So now with that, what we can do is put this information in here. We know that the length of the vector PQ is 4, and then cosine of pi over 4. So we get √2/2, and then 4 times sine of pi over 4. Don't forget your I and your j because we need a vector there. All right, and so we get 4 times √2/2, so we get 2 √2i plus 2 √2j. And now to find our moment M, we need to find the cross product of these 2 vectors. And we'll rewrite this in the same form that we had that one. So 2 √2, 2 √2. Now, what we encounter here is that the cross product, when we computed it with 3-dimensional vectors, or vectors that had I, j, and k component. These, because we're working in 2 dimensions, they still have a k component. The k component is just 0. So I'm going to set this up, and I'll let you all go through and actually do the computations yourself. They'll be simpler than the other cross product computations because the k component on both of our vectors is 0. So we can still put I, j, k, or you can use that formula. But now, remember to make sure you put these in the correct order. We're going to have 2 √2, 2 √2, and then 0. So 2 √2, 2 √2, 0, and then 0, -5, 0. And you go through and compute that cross product as usual, and that will give you the moment. And remember, this is a vector, so when you finish, make sure you have your I, j, your k. Whenever you have a cross product of 2 vectors, though, that does not have both of which are 2-dimensional vectors, so their K components are both 0, your answer is going to come out as, I mean, I could go through and compute it, but I'm going to let you all do that. It's something K whenever you have a cross product. And you all know that because a cross product of two vectors in the plane is going to give you a vector that's perpendicular to the plane. So that means we're going to get a vector that points in the K direction because PQ is in the XY plane and F is in the XY plane. So that means the cross product has to be something that points in the K direction. So you'll go through this and you're just going to get something K there when you compute that. All right, so try that cross product along with trying project 1 on page 736 of your textbook. And that's just determining whether some quantities that they give you, determining whether those are scalar values, like a dot product's a scalar. They're vectors, whereas a cross product is going to give you a scalar, or whatever quantity they're asking you to compute actually doesn't make sense. You can't do, say, for instance, a dot product of a scalar with a vector. If you want to do a dot product, you have to have two vectors. You same thing with the cross product. You have to have two vectors. You can't do a cross product of a scalar with a vector. So you'll look at those different things they list there and see which of those are scalars, which of them give you vectors, and which of the quantities that they ask for are actually meaningless entirely.